Welcome again in this video. Since we've done a lot of problems regarding limits, let us now apply these limits in solving the heart of what we call differential calculus, especially differentiation. Now, differentiation is the process of finding the derivative of a function. Well, mainly, the derivatives can be expressed in at least 6 of these notations that we have here in the box. So the first two of them would be the Lagrange notation, in which these two are the notations that are usually used in high school in your junior and high school days. Now the second one would be the Leibniz expression or notation. We have dy over dx, which simply means that the derivative of y with respect to x, and then there's the derivative of f of x with respect to x. So basically these two are just the same. We're just implying that f of x here is equal to y, and that's the Leibniz notation. And then the fifth one would be the Euler notation. We have d sub x of y. So basically we take the derivative of y with respect to x. And then the last one would be the Newton, which is a much less common notation that we used in differential calculus. And as you can see here, it has a y and then a dot at the upper part of this y here. So whatever the function is, you just add some dot on the accent, dot accent for that function, and you'll get the Newton notation for expression of derivatives. Anyway, in this case, we'll just be using most of the time 1 to 4 of this expression of derivatives. Okay, and now since we've talked about limits, we need to understand that the derivatives or differentiation vehemently applies limits. And in this case, what we have here is the limit of delta y over delta x as the delta x approaches to 0. And with that, if you take the value of delta y, you will get simply f, and then this is a 3-step rule that you've been solving for a million years in your high school. So we have x plus delta x minus f of x all over delta x, and that this expression at the above or the numerator would simply mean that it is the delta y or the change in y, and then the lower part here, the denominator will be the delta x. Of course, delta x approaches to 0. And what you will get there, if you will be evaluating that at a certain value, you will get m here, which means the slope. And with that, it can be concluded that the application or the very basic application of differentiation, when you take the derivative of a certain function, you're technically finding the slope of that function at that certain point that we're talking about. In this case, if we have a point that is C, FC, so we have here this point C, FC, and then there's this graph here in which that is our equation f of x. If I wanted to take the derivative of that f of x, then this is this blue portion here, that is the derivative. So most of the time the derivatives are not really that a straight line, but if you just have something like an equation that is of the second degree, then you'll be getting this straight line. But what I want to pinpoint is that since this is now the derivative of f of x, the value here that you will be obtaining substituting c would simply mean that you will have f prime of c, and f prime of c would give you the value of your slope, which is m. And with that, it can be concluded that differentiability implies continuity. So that's our food for thought. So before we proceed with all the rules, let's just remember that when a certain function is differentiable at a certain value of c or a or whatever that is inside of an interval ab, so for example this one and this one, all the points that are inside a continuous function, it implies that if you can determine a derivative of that function at a certain value along the domain of that function, then you'll be getting a continuous function at that certain point. Of course, it can be noted that almost all the equations can be differentiated. But of course, not all equations can have a value at a certain point. So you can have the equation being differentiated, but the whole domain, if there's a discontinuity, then at some point the derivative will not exist. Now let's move on with the rules of differentiation for algebraic and main trigonometric functions. So it should have been like algebraic functions only, but I wanted to add the trigonometric functions so that we can understand more when we can understand the higher order derivatives when we as this discussion progresses. So let's start with the first rule, and that's the very basic rule we have, constant rule. So whenever you need to determine the derivative of a certain function that is a constant, that is simply taking the derivative of a certain real value, let's say the derivative of 3 or 4 or 5, 6.75, any value that is not a real number, you will be getting 0. So that's it for a constant rule. And then we have the identity rule. So when we take the derivative of x or any independent function that we will be specifying, then you'll be getting 1 dx. Now I have to emphasize this dx here. If we're talking about the derivative of y, let's say y is equal to x, and then I wanted you to find the derivative, you will be answering something like y prime is equal to 1, and that's all for that. But if I have, let's say, the derivative of x, you should be answering something like 1 dx or simply dx. Well, because the derivative of this function must be expressed in terms of the differentiating variable here. And in this case, since this is already a topic in your differential equations, which we will be taking after the integral calculus, thing is, you need to add dx whenever you don't have any y prime here. But if you have y prime here, you don't have to add dx here, because literally y prime means that this is the change, something like the change in y over the change in x. So you don't have to add dx here because it's already written in a y prime expression. So be careful with that, since if you just answered here, let's say I need to find the derivative for the expression, and then you just answered 1, then it will be marked incorrect simply because it should be dx, since you can't see any y prime here. But if you answered for this expression, let's say y prime equals 1, then that's still correct. Now let's move on with the third and probably the most often used rule for differentiation, and that is the power rule. Now, power rule, we have a certain general expression of x, or the independent variable, raised to n. That is, n is a real number, and any power that you can think of, as long as it's not complex, as long as it's inside the number line. So all you have to do is to multiply this x to the n minus 1 to the exponent, or simply just put the exponent in front of that x and then subtract 1 from the original value of the exponent. So let's try doing that on this example. So 3/2 is our n. So based on this rule, I just need to place our exponent in front of the variable, which is x. So what I'll be having there is 3/2 and then x. So that's 3/2 multiplied with x, and then I need to subtract 1 from 3/2 based on our rule. So I'll be getting 3/2 minus 1, and let's just put some equal here. So with that, our answer can be simplified to 3/2 and then x, since 3/2 minus 1 would be equal to 1/2. So I'll be getting 3/2 x raised to 1/2. Now, let's proceed with the second example. By the way, since this is d over dx, I need to add some dx here, since that completes the equation or the answer for this problem. Now, since this one is in y explicit form, we call this the explicit form of equation simply because y is separated from x by an equal sign. So this explicit form of equation will be using, remember, if we have y here, it says here that the derivative will be using the Lagrange, and then the one that we solved before is using actually the Leibniz notation. So using the Lagrange notation, the derivative would simply be y prime is equal to whatever the derivative here. Now in this case, x must be expressed in this kind of form. But if you will be looking at this, that's actually something like a reciprocal of x to the negative 2. So with that, let's rewrite this expression into y is equal to x raised to negative 2, so that we will have a form that is, you can see here x and x here as well. So with that, then we take the derivative with respect to x, then we'll be getting y prime that is equal to negative 2, and then x, then negative 2 minus 1 based on this one, so we'll be getting negative 3. So you don't have to add the x since we already have y prime here. But you can simplify this further by rewriting this to negative 2 over x cubed. Well, simply because it's more appropriate just to look at it where x cubed is the denominator, just to remove the negative exponent here. But of course, this is still correct, but this one looks better. Okay, now let's proceed with number 4. So we have there the constant multiple rule. It says here in this, I forgot the that's fine. Now, for the constant multiple rule, it says here that if you have a function that is multiplied to a certain constant, all you have to do is to take that constant and then multiply it to the derivative of your function. So in this case, we have an example that is 4x squared. So what we have here is 4 being our constant. So based on the rule, I just have to write 4 and then multiply it with the derivative of our function, and the function here is actually fx squared. So with that, I need to take the derivative of x squared, which is basically from our previous rules, which is the power rule. So we get 2x. So with that, I'll be having an answer that is 8x dx for this problem. Now, here's another constant multiple rule. Now, if you notice here, the derivative or the function is being evaluated with respect to t and not x. Now, there are a lot of times where, of course, in your higher engineering, that you'll be encountering problems in which we will be differentiating functions, not simply with respect to x, but of course, sometimes it is with respect to time, with respect to the area, or even length or temperature. So with that, you'll be encountering problems in which the differentiating variable is not expressed in terms of simply x, but other letters of the alphabet. Sometimes it's even more complicated when Greek alphabets are involved. So with that, you have to understand that when we have this kind of expression, just have to look at the variable that is after the d term. So we have here t. So that simply means that we have to differentiate this with respect to t. It's like just assuming that this, if it is x, then that's just 1/2 x raised to negative 3. So with that, the derivative of this expression with respect to t will be 1/2. Just copy the constant, and then the derivative of the function that's left, that is t raised to negative 3. So I'll be applying again the power rule. So that is negative 3 minus 1, that is negative 4. So the answer here would be negative 3/2, and then t raised to negative 4. And then since this is d over dt, I need to add some dt here just to complete our solution. I can also simplify this, or rewrite this in as something like 2 raised to the 4, just to bring down the negative 4 to the denominator. And let's proceed with number 5. Of course, I'll be giving you something like the one I used to solve before, like 25 problems in one sitting, just to refresh all your minds with this. These are just examples to aid you in understanding the rules that we have. Okay. So number 5, we have sum and difference rule. This is probably the easiest one to understand. It simply means that if you have a function that is added or subtracted, you just have to take the derivative of each term for that, and then just copy the operation that you have. So let's try doing this for letter A. So for letter A, if we need to find the derivative, that's just simply using the f prime of x, since this is given by f of x. So the derivative is f prime x. That is equal to the derivative of the first term, the second term, and then the third term. So if we take the derivative of 3x squared, that's just simply a combination of constant and power rule. So what we get there is 3, and then we have here 2x, and then plus 1 over x. When you differentiate 1 over x, we can simply rewrite that first into x raised to negative 1, and then negative x raised to negative 1 is much easier to differentiate than 1 over x. So what we'll be getting is, we'll be using positive since this is positive, and then x raised to negative 1 would be, so x raised to negative 1 would be negative 1, then x raised to negative 1 minus 1, which becomes negative 2. And then we can also remove negative 1 here, since just multiplying it with x will simply give you an x value. Or let's just use negative x raised to negative 2. And then we have negative 3, that is actually minus 0, since the derivative of 3 is 0. So what we'll be getting here by rewriting the equation is a derivative of this function. So what we'll have here will be 6x, and then that would be minus 1 over x squared. So this is the final answer for this question. This is already correct, but of course you have to simplify it further to make it look better, and to make it shorter than this. Okay, and of course it's more mathematically pleasing. I call it mathematically pleasing. Now let's proceed with the second example. Here we have to take the derivative of kx raised to 1.7 minus jx. Now in some cases you might feel intimidated simply because you're quite seeing this k and j, and what you'll be seeing from now on would be a lot of letters in the alphabet. And what you have to remember about these letters coexisting with these x's and y's would simply be that these letters are just treated as constants. Of course, it should be specified in any kind of problem, but generally, when you have letters that are coexisting with a function that you need to be differentiated, usually they are treated as constants. And especially if you have your dx, then you need to simply just look at x, since that's the variable that we need to differentiate, and just forget the rest of it. Just treat them as constants. So when we say we treat others as constants, it simply means that it could assume values that are constants. For example, 2, 3, 4, 5, 1.7, negative 5, any values of that. And then since they are constants, you will be using the differentiating rule considering that they are constants, even though they are letters. Now let's just have something like k. Of course you don't have to do this in problem solving, but I just wanted to specify that k and j are elements of real number, and they are constants, just to dispel the confusion that may arise from this. Okay, so with that, let's try to evaluate this or differentiate. So this is actually a constant multiple rule, and multiplied with some power rule, just like what we did before with the x squared. So with that, The answer here would be simply k, since that is a constant, then multiplied with the power rule. So what we're getting is 1.7x, and then 1.7 minus 1 would be 0.7, and then minus, you have to take this minus jx, since j is constant and x here would be identity rule, so we'll be having j, and then the derivative of x is simply 1. So our final answer would be 1.7 kx 0.7 minus j. Of course, you can just write k and then multiply with 1.7 x raised to 0.7, but it's generally preferred that you write the numbers first and then the letters. Sorry, I forgot to add some dx here, so don't forget it, since this dx is very important. Actually, not just for j but for the whole expression, so you add some dx. So dx is very important for this expression, since it is given with d over dx, or the Leibniz notation. Let's proceed with product rule. Since we do have sum and difference, of course we have to have this product rule. Now, for product rule, what you have to consider always, like finding the f of x and then g of x. So after that, it's a piece of cake, okay? So in problems where you are multiplying, there are a lot of ways that you can select f of x and g of x, but it's always up to the person that solves the problem. It's based on their perspective. So if you find this particular equation easier, then it's your choice to select what will be f of x and then g of x. Now, for the sake of this problem, let me just solve this in a very detailed manner. We have f of x. Let's just label these parts, okay? We have x to the a, and then we have g of x. That is, of course, g of x would be any portion that is left in this equation. So what we have there is 4x cubed. Now, in our equation, we need here the derivative of g and the derivative of f function. So what we get here is the derivative of x, of f of x. So I think this will be your first time seeing a letter that is, x raised to a certain letter. So remember, the general rule for power rule is that if this is a power or an exponent, you just have to place it in front of x and then subtract 1. So it's like we're rewriting the general for power rule. So with that, the derivative of x to the a would simply mean that we have a and then x raised to a minus 1. And this is what we always do with exponents. And then for g of x, we need to take the derivative. If you take the derivative, that is just a constant in power, so we get 4 times 3x squared, so we get here 12x squared. Now, we've already completed these those things that we need to rewrite the expression. So now we'll be rewriting the expression to get the final answer. So with that, y prime, we'll be using the Lagrange notation. So y prime, it says here that we need to copy f of x. So what we get here is x to the a, then multiply with the derivative of g of x. So in this case, that is 12x squared. So we have 12x squared, and then we add, since this is product, so we add g of x. G of x here is 4x cubed, and then we multiply it with the derivative of f of x, which is ax raised to a minus 1. And then the last part, as always, would be simplifying our equation. Let's just do it here. Probably I will not mess up the previous one. So y prime would be, let's just multiply this, so we have 12 and then x. Since they have the same base, we just have to add the exponents. So we have a plus 2 and then plus. So we also have the same base here, that is So we'll be having 4a and then copy the base. So we have 3 and then a minus 1. We add them since this is multiplication. So what we having here is, since we have 3 plus a minus 1, so we get 2 plus a. So this is the final answer for this expression. So that's basically how product rule goes. So let's try letter B. So I will not be doing this again by enumerating all of this stuff, f of x, g of x, since these are just a review of your high school. So if I would take the derivative of this function, I'll be having this kind of f of x here, the square root of x, and then g of x being x squared minus b squared. Now b squared, of course, it will also take the constant assumption here, so whatever this is, it acts like a constant. So now let's try differentiating. So it says here that you just have to copy the first term that you designate as f of x and then take the derivative of those that are left. So with that is 2x, and then since b squared is a constant, I don't have to take the derivative of it since it will be 0. I mean, if I would be differentiating it, then that is 0. And then we add, so we need to copy g of x, so we have x squared minus b squared. So I just copied it and then take the derivative of f of x. That is simply square root of x. Now, remember, square root of x is actually equal to, this portion here is actually equal to x raised to 1/2. So with that, if we wanted to define the derivative using power rule, what we'll be getting is 1/2, then x raised to 1/2 minus 1, which gives us negative 1/2. So finally, what we'll be getting here is 2x. This one is 1/2, and then this one is 1. So what we'll be getting here is 3/2, and then plus. So we need not to expand this any further. So, or you want to expand if that suits you well, but you don't have to do that. So I'll just be using something like 1/2 square root of x just to bring down the negative sign here, and then multiply it with x squared minus b squared. So this is the answer. By the way, if you'll be writing this as your answer, you also have to equal this to f prime x, since that is the Lagrange notation of the derivative of this function. Now, if you wanted to distribute this further, you can do that. That's the correct. Since differentiation actually doesn't have a fixed rule that specifies that all the solutions should be like this, and there are varieties of solutions that you can present in differentiation. That's why it's a very flexible math, and for as long as you're quite sure of what you're doing, then you won't get you won't get lost along this solution. Now let's proceed with the quotient rule. Quotient rule is by far, of all the 4 operations or arithmetic operations, it is the most complicated, and usually students like to avoid this quotient rule, but this is actually easy. You just have to remember that whenever you have a function that is rational, that is f of x over g of x, you just have to copy the denominator and then multiply it with the derivative of the numerator, subtract it by the numerator multiplied with the derivative of the denominator, and then divide all by the square of the denominator. Now let's try using that on our first example here. Now for the sake of understanding, let me just first dissect all of these into g of x and f of x. In this case, we have f of x being equal to the numerator, that is x plus square root of x. Now we also have g of x equal to the denominator, which is x to the n. So now if you will be taking the derivative of f of x, because we need it based on this equation, we'll be getting let's use blue. So we'll be getting f prime of x that is equal to 1 plus, since this is actually x raised to 1/2, then this becomes 1/2 x raised to 1/2 minus 1, which becomes negative 1/2. And we can also rewrite this in terms of 1 plus 1 over 2 square root of x, but for now let's just leave it like that. And then we need to take the derivative of g of x, that is simply g prime of x, that is equal to n, then x raised to n minus 1. So this is basically the power rule that we use. So with that, let's plug in all the values that we've obtained from based on our formula here. We have g of x, so just copy the denominator, x to the n, multiply this with the derivative of the numerator, so we have 1 plus, and then now I'll be rewriting this 1/2 x to the negative 1 out in a more beautiful way. So I have 1 divided by that is 2 square root of x. Well, sometimes you can also do rationalizing, but in this case I won't be doing it. Then minus, so we have f of x, that is x plus square root of x, and then we need to multiply this with the derivative of the denominator, that is nx raised to n minus 1, then divide this all by, we divide this by the square of the denominator. So we have x to the n being the denominator, so squaring it will have it multiplied with 2. So that is our answer for this particular, so we add here the x. So for this problem, this is our answer. Well, you can also simplify that by distributing this stuff, but I won't be doing it since it won't fit inside our screen. But this is, I just wanted to show you how this works in a more in a general way or general form. But if we will be simplifying this further, let's just do it anyway. So first is that most of the time you will be able to cancel out some factors here. Now I'll be factoring out x to the n. So in the first term, we don't have to do anything since it's already factored out. So in the second term, so this is the first term. Now for the second term, as you can see, there's this x to the n minus 1. And if I'll be taking out x to the n there, what I'll be getting is this one is multiplied with, so this can also be written as n times x to the n minus 1, n times x to the n times 1 over x. So in this case, what I'll be left with is n times 1 over x. You can check it out again. If you distribute this x to the n to that portion, you'll be getting n times x to the n times x to the negative 1, which becomes n x to the n minus 1. Then we divide this by the denominator, which is x to the 2n. So here we have x to the 2n, and in this case we can cancel out n here, so that we'll be left out with n alone. And then for some reason we can just multiply this, distribute this latter term, and then I think that's all for this case. So we have 1 plus 1 over 2 square root of x, and then we have there x times n times 1 over x. We have minus n because this this results to 1, and then we'll be getting minus square root of x over x, and then this shall be divided by x to the n. dx. So we add dx always. I'll be rationalizing the denominator, so I'll be getting square root of x over 2x, and then minus n minus square root of x over x. So this can be further simplified by adding. Actually, guys, you can see there, we can add these two here. So with that, it's like 1/2 minus 1. So what we'll be getting there is negative 1/2. So we have 1 minus n minus 1/2 square root of x over x, and then divided by x to the n dx. So this is how you simplify this expression here. But I mean, in cases where you have a very complicated answers, I won't require you to like simplify them just for the sake of having a more simplified answer. But in cases where it's a lot easy to simplify, like this one is considered easy, then you must do simplifying for that. Okay, now let's move on with last of the example, which is the derivative of this expression with respect to m. So in this case, we're not dealing with the independent variable being x. Sorry, we're dealing with the independent variable being m here. So we just have to take this like x. Now let's follow the rules here. It says here that we need to copy the denominator. So what we'll be getting here is 1, then divided by the cube root of m. So I just copied the denominator and then multiply this with the derivative of this upper portion, or the numerator. So if I'll be taking the derivative of that, let me just use another color. So in this case, 2m to the 4th, when you find the derivative of that, you'll be getting 2 times 4m cubed based on the constant and power rule. So I have here 8 and then m cubed. So I just directly obtain the derivative for that. And then m is like a identity rule, so we have here 1. So that's the derivative of our f of x, and then we need to subtract this with f of x. So we have 2m to the 4th minus m, and then multiply this with the derivative of our g of x. So I hope the space will be enough. So let me just take the derivative of this one. Now this 1 over cube root of m can be rewritten as 1 over m raised to 1/3, which can also be rewritten as m raised to negative 1/3. So I'll be using this m raised to negative 1/3 to simplify the for it to have an easier rule that can be applied, since in this case the power rule can be applied in this case. So I'll be having negative 1/3 then m. So negative 1/3 minus 1 would be equal to negative 4 over 3. So we have here negative 4 over 3, and then we need to divide all of these by the square of the denominator. So the square of the denominator would be 1 over the cube root of m quantity squared. So we have 1 divided by a cube root of m squared. So that's how it goes for the denominator. Now you can simplify this further. I won't be doing it anymore. You can just simply distribute all of these, or factor out 1 over cube root of m here, and you can simplify this equation just like what we did here. And I want you to do that as a practice, so that you can always practice your algebra skills you've learned. Anyway, so that's it for the quotient rule. Now let's proceed with I think this is the most important of all the rules. Well, of course everything is important, but this chain rule and general power rule is like the bread and butter of your differentiation. So when you understand chain rule enough, you you're able to like differentiate almost anything. The only reason that makes it difficult is that if you just started to understand chain rule and general power rule, and then you'll be encountering problems that require it will be very difficult for beginners. But you're already considered not beginners since you've already had this in your senior high school. So anyway, so let's have this. The derivative for the chain rule, we have the derivative of f of g of x. So this f of g of x is actually a composition function. And when we take the derivative of that composition of function, you can see here that you need to take the derivative of this whole function here. We express this whole function here as f of x. You take the derivative of that, and then you differentiate or take the derivative of what is inside. Now, the technique that I'm teaching to my students is that you look from the outside going inside. It's like you always take a look at the general form or general equation, and then slowly, one by one or step by step, you differentiate what is inside that function, that composition of function. Of course, you should always remember that this is only applicable for composition function. Now, for the general power rule, this is just an extension of the power rule. Well, actually, the power rule is derived from this general power rule. Now, before we used to have x here, now we're considering f of x, meaning it can assume any kind of function. It's just not x. Sometimes it could be like x squared plus 4, 5x plus 9, any function that is, differentiable. So if it is raised to a certain real power n, you can just take use the power rule. You have n here multiplied with f of x, then n minus 1. So in power rule, we stop there, just add the x, and that's all. But in this case, since it's general power rule and it applies the chain rule, you also have to take the derivative of what is inside here, meaning you have to take the derivative of the function itself. Now, we're also doing that in power rule. We're actually doing that again. If you can see here, x raised to n would be n x raised to n minus 1, and then the derivative of this x would be dx, or simply 1, like 1 dx. So we're simply applying the same principle here in our general power rule. Now, to understand it better, let me just use this first example as first example. We have here, as you can see there, 2x cubed minus 3 squared, quantity squared, plus x to the b plus x raised to 8.6. So we need to take we need to find the derivative for this. Now, this is a combination of almost all the rules that we have discussed. First is that this is a sum, since we have a separating operation here that is plus. This is a general power rule because we have a function here. And then, of course, since it is a general power rule, it is indeed a chain rule. So with that, let's dissect each of them so that you won't get confused. I'll be starting my solution with, let's just use one color. I'll be starting my solution with a blue color for 2x cubed minus 3 quantity squared. In this case, the derivative of this function is simply applying the general rule that we have. Since this is the function, this is actually the function that we have, f of x. So it says here that if you have an exponent, you just have to do this and then take the derivative of this function that's inside. So I'll be having the derivative of this 2x cubed minus 3 would be 2 times 2x cubed minus 3, and then 2 minus 1 would be 1, and then it's not yet done. We need to take the derivative of what's inside here, so we get 6x. So that is 2 times 3x squared. That is 6x squared, and then minus 0. So the first, or the derivative of this function here, is this one. Now we add, since the operation is addition, and then we take the derivative of this. Let's use like orange. So in this case, we need to take the derivative we apply the same principle. So we have 8.6 and then x to the b. Just have to copy it first. So we have x to the b plus x raised to 8.6 minus 1 would be 7.6, and then multiply this with the derivative of this function here. Let's just use g of x. So derivative of this g of x would be x to the b, so we have b x to the b minus 1 and then plus 1. So you can expand this further, since this is very easy to expand. Now I won't require you to expand this because it is you can see this one is in decimal exponent. So with that, the answer can be written as this is equal to 6 times 12 times 24. So we have 24x, 3 plus 2, we have 5, and then minus, so we have 18 here times 2 would be 36, I guess. So we have 36x squared, and then let's just copy this since we can't do anything about it anymore. So okay, and then don't forget to write dx. Need to add some dx here so that it finalizes our answer. So we have dx. Okay, so this is our answer for this problem. Let's do some rectangles here so that you can see the answers that we have had. Okay, so dx is very important since we're expressing this in terms of the d over dx, which is the Leibniz notation. So now we're done with letter A. Now let's start with letter B. If you wanted to solve B beforehand, then you can just pause the video, solve it, and then check it out after I've solved it. Okay, so let's do this one. We have y prime that is equal to, now if you can notice here, when you solve when you're differentiating, you always have to look at the equation first before doing something, okay, before applying the rules. Now you have to analyze here that we have here these two functions multiplied with each other. This one is something like f of x, and then this one is like the g of x. And as you can see here, it's like f of x times g of x. And by that virtue, in general, we're simply multiplying f of x and g of x. So at first, we look at the outside. As you can see there, the general the general form of these two functions, or the function itself, is like a product of two subfunctions f of x and g of x. So in this case, I'll be applying a product rule since this is just multiplication. And to do that, I'll be having x plus 4, just copy this one, squared, and then take the derivative of this function. Now I'll be taking the derivative of g of x, so I have here 6, so we need to multiply it by 6, and then x plus 3, and then that will be 6 minus 1 based on our general power rule, and then multiply this with the derivative of what's inside, and the derivative of x plus 3 would simply be 1 plus 0, so that's just 1. And then based on the product rule, I'll be adding and then taking the derivative of the second, but first let me just copy the second expression, and then take the derivative of this function here. Let me just rewrite it. So the derivative, let's just another one. The derivative of x plus 4 squared would be times 2, and then x plus 4, 2 minus 1 would be 1, and then times 1. So therefore, the derivative of this expression here would be y prime equal to, we can't do anything about this, we won't be expanding this, so let's just use 6 since it's constant, and then write this in a logical way. and then plus, this one is, we can have 2 and then x plus 3 to the 6, and then, let's write x plus 4 first. Just to be, parallel with this. Now, if you wanted to factor out 2 and then x plus, 2 and then x plus 4, and then x plus 3 to the 6, to the 5th, you're free to do so, simply because you can factor them out and then multiply it with, what's left here would be x plus 3. Let's just start with this. So what's left here would be 3 and then multiplied with x plus 4, and then the one that will be left here out would be plus x plus 3. Now this can be simplified further. So as you can see there, we can this will be equal to 2 and then x plus 4, and then it's equal to 2 times x plus 4, and then we have x plus 3 raised to the 5th power, and then we multiply this with, this will be 3x plus 12. So 3x plus x would be 4x, and then we add, since this one would be 12 plus 3 would be 15. Okay, so we already have y prime here, so you don't have to add some dx here. So this is your final answer. And this is the most simplified form for that. I hope I got the correct addition for that. 3x plus x will be 4x, and then 12 plus 3 will be 15. Okay, good. It's actually overcrowding our space here, and we still have one. Now let me just transfer this probably somewhere here. Let's just transfer this to some place here. Okay, good. So we have C here, and let's label it letter C for quotient, for chain rule. Now as you can see here, this is a rational expression, and based on our general rule, we need to inspect the equation first and look at the general property of that equation, and in this case it is a rational expression, and by virtue of having a rational expression where this can be the numerator can be set as f of x, this can be f of x, and then the denominator can be g of x. So with that, it follows that it's gone anyway. So with that, it follows that we will be applying quotient rule here, and then use other rules that will be, that needs to be applied along the process. So I'll be taking the derivative of this function. I'll be using this f prime x, since that's the Lagrange notation for that. And then for product rule, I'll be copying the denominator first, so that is 1.7x raised to 2.4 minus 2x and then cube. So that's the first thing that we need to do using quotient rule. Quotient rule for our quotient rule. And then we take the derivative of the numerator, so that will be multiplied with the derivative of this x to the 4th minus abc would simply be 4x cubed. Why? Simply abc is a constant, so whatever the constant is, if it is a constant, even though you will be multiplying that or dividing, the answer will still be a constant. The derivative would still be a constant. And then, since this is a quotient rule, will be subtracting. So we subtract, and then we first copy the numerator, so x to the 4th minus abc, and then multiply this with the derivative of the denominator. So the derivative of the denominator would be this one. Now the derivative of this denominator is simply in general power rule. So we'll be applying the general power rule and then take the derivative using this chain rule. So we'll be having 3 and then 1.7 x raised to 2.4, then minus 2x, then raised to 2. And then we take the derivative of what's inside here. So I'll be having 1.7 times 2.4. So I'll be using the calculator to multiply that. We have 4.08. So we'll be having here 4.08, and then we have x raised to 1.4 since it's already subtracted by 1, and then minus 2. So that is the derivative of what is inside here. Okay, and that will be divided by all the expression will be divided by, of course, the square of this denominator. So you just be having 1. Let's use another color. So we'll be having 1.7 x raised to 2.4, and then minus 2x, and then raise this to the square. So that is cube, so we get 6 here. So in that case, this is our final answer. Sometimes we can still simplify this further. As you can see here, this one is square, this one is cube, so we can factor out square here and we'll be left. So factoring out square will be left out with we cancel this out. We'll be left with 1 here since we're factoring out 2, and then since we're removing 2 here, we'll be left with 4. Okay, so in short, the answer can be rewritten as this is the simplified form, I guess. So we have 1.7x, okay, so this is our final answer for this equation here. So you can also, if you wanted to simplify further, the only thing you can do here is to use some formal method here to evaluate this, and then distribute this to, and then add, if you can add something, and divide it by this function. But basically that's all that's left. I won't be requiring to like simplify this further in a way that you'll be having just terms here and no multiplication. I am actually allowing that, so I think I'll be allowing answers starting from this, and any answers that will be simplified further from this. Okay, why? Simply because my main concern is the way you differentiate, not the way you simplify. Of course, that's very it is a required skill that you should know, that basically you're in engineering and you already have had your high school days, so you should always, I'm assuming that you already know how to simplify such kind of algebraic equations. So given that, I won't be requiring you to like simplify this in a very, very simplified form, since it's not of my concern. My concern is how you differentiate. So starting from this, it's already like the answer. Okay, so whatever answer that you will be getting starting from this by simplifying would also be correct. Well, for as long as it's correct. Now we're pretty much done with all the operations, algebraic operations, and the additional that we have here would be, actually, trigonometric functions are transcendental functions. So we'll be having a separate topic for that. But in this case, since these are basic trigonometric functions, I wanted to introduce this beforehand before we use we discuss transcendental functions. So in any case, this will be used in explaining higher order derivatives and implicit differentiation. So I think, and when you get gotten to transcendental functions, it will not be as difficult as it may seem when you know at least these basic trigonometric functions. Okay, so there are 6 trigonometric functions that we know, and this is in trigonometry because it simply has this, when we have this unit circled, they obey a certain rule where the hypotenuse would always equal to 1. So in that case, we get the cosine of x, that is, when we talk about cosine in trigonometry, we're referring to that value of the adjacent, the adjacent leg of a triangle to the angle x. Well, for the sine, we have there the opposite, and then the tangent would be the ratio. So all of these stuff that we have cotangent, secant, cosecant will be the reciprocal functions of those 3 main that we've talked about. So the derivative of sine x would be cosine of x. The derivative of cosine x would be negative sine x. The derivative of tangent x would be secant squared. Cotangent x would be negative cosecant squared. Secant would be secant tangent, and then cosecant would be negative cosecant cotangent x. So this is very easy to remember, but the thing is, you might get confused with the negative signs here and the positive. So the clue here that I'll be telling you would be that when you're differentiating something that has a co, that equates to a negative derivative. So remember this, okay? For example, I'm differentiating cosine of x. Since it has a co-term, the answer would have a negative. The derivative would have a negative. Same goes for cotangent. It has a co, so the derivative would be negative cosecant. And then for cosecant, it has a co, so the answer, the derivative would be negative. Okay, so that's all you need to memorize this, and then let's solve for these problems here that we have. So we just have 3. I'll be hiding those rules. I hope you've memorized it already. So we have a y equals cosecant 3x plus 3. Now, since we've already discussed chain rule, I would say that trigonometric functions are those functions that would always employ chain rule. Since basically when you take the sine of x, you're actually referring to a compositional function wherein you take the sine of x or sine of a certain function. So in this case, I'm taking the cosecant of a certain function, 3x plus 3. So with that, based on our chain rule, we need to find the derivative of this whole term first, and then take the derivative of what's inside. So this is like the f of g of x. So we need to take the derivative of f of x first, and then g of x. So with that, y prime would be equal to, so as what I've mentioned before, when we solve something like chain rule, you start with the outside going inside, and the outside, something like the outside function here would be cosecant. So when you take the derivative of cosecant, remember, the derivative of that would be negative cosecant and then cotangent. So it's something like that. Now, what's inside here would simply not be x, since the rule says here that it should be x. That is true, but that is x simply because the function here is x. Now, if it changes, for example, this one, it's not x, it's 3x plus 3. So you'll be writing 3x plus 3, okay, instead of x. Remember, that's very important. Let's compress this. Okay, so we have 3x plus 3, and then cotangent 3x plus 3. Now, I usually encounter students who would write negative cosecant x and then 3x plus 3. So this actually is very wrong, simply because it breaks the rule. As you can see, you won't have any cosecant x here, simply because there's no cosecant x here from the equation. Yeah, what you have here is 3x plus 3. So you should you'll be seeing 3x plus 3 on the inside or the compositional function of that trig function. Okay, so with that, that doesn't end yet, simply because it says here that if you have a composition function, you need to take the derivative of this, and we've already done that. That is negative cosecant cotangent. But you also need to take the derivative of what's inside, and what's inside would be multiplied with what we have obtained before. So that is simply, let me use another color. So the derivative of that would be 3, since we have 3x, and then plus 0, so we have 3. So therefore, the final answer here would be that y prime is equal to negative 3 cosecant 3x plus 3, and then we have cotangent 3x plus 3. Now, I don't want to see anyone distributing this 3 with this, making this something like 9 plus 9x plus 9. That's very wrong, since this 3 is actually multiplied with the whole function here, and it's like you need to take this cosecant first before you multiply this with 3. So don't do that, okay? You're making Einstein angry. Anyway, so this is the final answer, and actually that kind of I don't know, that kind of mathematical expression actually appeared on your first activity. I remember if you have that cosine, I think the cosine. So okay, so that's the answer for A. So we move on with B. Now this B is I personally love this kind of equations. I did this, but sometimes I still have my favorite equations that I solve. So I really love this because it actually gives you a glimpse of the actual chain rule and composition function. Now, remember, for chain rule or for composition function, as what I've mentioned before, we always start from the outside. And from the outside, what we can say is the cosine. We take the cosine of the sine of the 2x. It's like a composition of two functions, something like f of g of h of x. It's something like this, okay? And of course, if you have something like that, you need to take the derivative of what's outside, and then you go to the inside. So we have your cosine, so that's just taking the derivative of cosine. So derivative of cosine, since it has a cos, so there'll be negative sign, and then this negative sign would be what's inside of that cosine. So just copy it. We have sine of 2x. So don't be bothered with the expression that you'll be getting, since you'll be encountering much more complicated than that. So it's like taking the negative sign of the sine of 2x. But you're not yet done, since as what I've mentioned before in our chain rule or composition of functions, you need to also take the derivative of that. So since we've just obtained the derivative of what's outside, we enter, or we proceed with what's inside, and what's inside here is sine 2x. So with that, we multiply with the derivative of sine 2x, that is inside of cosine. So the derivative of sine 2x would be cosine of 2x. Okay, so that's for the second derivative. I mean for the second function derivative. And then you already done that cosine 2x. Now you enter again on the inside, so what you'll be getting here is 2x. So you'll be multiplying that with 2. Okay, so as you can see here, we have something like 3. We have the sine, which is the outermost layer of that function, and then we proceed with the inside. We have cosine 2x and then 2. So finally, our answer would be f prime of x, that is equal to negative 2, and then sine of 2x, and then multiplied with cosine 2x. So you can no longer simplify this. Okay, I have to specify that because some may get confused. They will be multiplying this or just probably they will be placing this cosine to x inside this, so that's very wrong. Okay, remember this is actually multiplication, so it's not, you can perform that kind of operation. So I think we're done with the last one. So this one is something like a quotient rule with secant x squared at the numerator and then tangent x with the denominator. So let's use the notation for Lagrange since it's given as g of x. So g prime of x is equal to, now we'll be using quotient rule first. So we copy the denominator. We copy the denominator and then take the derivative of our, I don't think I'll be having enough space here later, so let's just move it somewhere here. Okay, so the derivative of the numerator would be, let me use another color, so that is secant x squared. So remember, the derivative of secant would be secant, and then you just copy what's inside, x squared, and then tangent x squared, and then you take the derivative of what's inside. So you have here, multiply this, all of this with 2x, and we're done with f prime x. So this whole term here is the f prime x, and then this one is g of x. And now since this is quotient rule, so we'll be subtracting, and then we take secant, we copy the numerator and then multiply this with the derivative of the denominator, and the denominator would be tangent x. So the derivative would be secant squared, and then that is x and not x squared. Okay, since this has x here, and then we divide this with the square of our denominator, that is tangent x. So we have here tangent squared x. Now if you're squaring this tangent, you can also something like write tangent x and then squared. That's the same as tangent squared of x. Now this one is different. Okay, that is not equal to tangent squared x. Since what this denotes is that you're squaring x here, not tangent. It's like something like this, okay? And it's different from this one. Okay? So I don't think we can simplify this further, but you can just write 2 in front of it, and then you're done, I think. Okay, so this is actually already the answer. Well, I don't think you can still simplify this, but this is generally the answer for that problem. So it's quite long, but basically we're just applying just 1 or 2 rules right here, or 3 probably. So don't get intimidated with how long your answer is. Just apply the rules, and even though you'll be getting a very long answer, for as long as you're applying the rules, then that will still be correct as long as you'll be applying the rules. Okay, so I think that's all for the properties of our basic trigonometric function, yes, and of course the algebraic functions that we've already discussed. So I'll be giving you a lot of examples for this, like the limits. I'll be solving at least 10. Well, I wanted to solve more complicated problems, so I will be limiting it to like 10 or 15. So yeah, and then you can practice those easy problems in your books that you have, or the module that was given to you. Okay, so with that ends this video. I hope you'll study well, and then for the next one or next 2 videos, I'll be uploading something like the higher order derivatives and implicit differentiation, which is the peak of this discussion. I think for you that will be the most difficult part for preliminary, but yeah, we'll get through it. Okay, so thank you.